it on your phone, your laptop, your big screen TV, and it just works? Well, today we're going to pull back the curtain on the magic that makes that possible. It's called media transcoding, and it's the invisible engine behind pretty much all modern video streaming. It really all comes down to this one big question, right? You've got this one beautiful, high-quality video file. How in the world does a service like YouTube or Netflix get that single file to play back perfectly for millions of people on thousands of different devices, all with totally different internet speeds? The answer is a really clever engineering process of digital transformation. We call it transcoding. You can think of it as the art of taking that one master file and creating a whole family of different versions, each one custom built for a specific device or connection. So here's how we're going to break it all down. First, we'll dig into that core problem. Then, we'll learn the lingo you need to know. We'll look at the command line tool that powers literally everything, see how it works at massive scale in the cloud, and then wrap up with the big decision every video engineer has to make.
Okay, let's kick things off by really digging into the core problem here, getting one video to play perfectly for everyone, everywhere.
At its heart, media transcoding is basically a factory. You feed it one high-quality master video, your source file, and it spits out a bunch of different versions. You'll get lower resolution versions for small phone screens, lower bitrate versions for people with slower internet, all of it designed to make sure everyone gets a smooth, buffer-free experience. Now, here's a really crucial point that people often get mixed up. You'll hear the words encoding and transcoding. Encoding is what you do the very first time, taking raw video from a camera and squishing it down. But in the world of streaming, like when you upload to YouTube, we're almost always transcoding. We're taking a file that's already compressed, like an MP4, and converting it into all those other necessary formats.
All right, let's move on and build up our vocabulary. To really understand how transcoding works, and more importantly, how you can control it, you've got to be able to speak the language.
First up is the codec. The easiest way to think about a codec is as the language the video is written in. It's the set of rules, the algorithm, that's used to compress the video file to make it small enough to send over the internet, and then decompress it for playback. H.264 is the old reliable, the most common one, while newer ones like HEVC give you better quality for even smaller file sizes. So if the codec is the language, the container is the box that everything comes in. You see, a file like an MP4 isn't just the video, it's a package deal. It's a container that holds the compressed video stream, the audio stream, maybe some subtitles or other metadata, all wrapped up and synchronized together.
Bitrate is all about data. It's a measurement of how much data we're using for every single second of video. As you can probably guess, a higher bitrate means more data, and that usually means higher visual quality, but it also means a bigger file. Simple as that.
And then there's resolution, which is probably the one you've heard of the most. It's just the number of pixels, the little dots of light that make up the picture. More pixels, like in 1080p or 4K, give you a sharper, more detailed image. When we transcode, creating versions with different resolutions is one of the main things we do.
Okay, now for a concept that senior engineers get really obsessed with, the GOP, which stands for Group of Pictures. Think about it. When you skip forward in a YouTube video, it doesn't just jump to any random frame, right? It jumps to specific points. Those points are full pictures, called iframes. The GOP size tells us how far apart those full pictures are. A shorter GOP means you can seek around more accurately, but it makes the file a little bigger. It's one of those key trade-offs engineers are always trying to balance.
So let's do a super quick recap. We've got the codec, that's the language. The container, that's the box. Bitrate, that's the quality. Resolution, the detail. And the GOP, which structures it all for smooth streaming. It's the combination of these 5 things that gives engineers total control over the final video.
So we know the lingo, we understand the concepts, but what's the actual tool that's doing all this work? Well, that brings us to FFmpeg, the true unsung hero of the entire video world. FFmpeg is this incredible, free, open-source tool that you run from the command line. It's the engine that's running behind the scenes at YouTube, at Twitch, pretty much everywhere. As a back-end developer, your job isn't to sit there typing out FFmpeg commands by hand. Your job is to build the automated systems, the cloud pipelines that call FFmpeg to do all the heavy lifting for you. And being efficient is everything. A junior developer might write a script that processes the 1080p version, then the 720p version, then the 480p version, one after another. But a senior engineer knows how to tell FFmpeg to create the entire set of videos, what we call an adaptive bitrate ladder, all in one single super efficient pass. Let's take a look.
Okay, let's break down a couple of key parts from that big command. First, you see something like -G48. That's us setting that fixed group of pictures we just talked about. We're telling FFmpeg, hey, I want a full iframe every 48 frames. If your video is, say, 24 frames per second, that gives you a perfect, clean breakpoint every 2 seconds, which is ideal for chopping the video up into small chunks for streaming.
And then you have this, the var stream map flag. This thing is pure magic. It's what tells FFmpeg to take all the different outputs you defined, the high-res video, the low-res video, the audio, and bundle them all together, creating a single master playlist file. That playlist is what you give to the video player so it knows about all the different quality levels it can switch between. It's incredibly powerful and saves so much time. So running a command on your laptop is one thing, but how do you process thousands or even millions of videos? Well, that's where the cloud comes in. It lets you take this single command and turn it into a massive, automated, global factory. Look, running your own fleet of transcoding servers is a nightmare. Trust me. That's why almost everyone turns to managed services from the big cloud providers. AWS has Elemental Media Convert, which is an absolute beast. It's what broadcasters use. Google Cloud has a simple transcoder API that's fantastic for automation. And used to have Azure Media Services, but they're actually retiring that one. And this slide right here, this really nails the fundamental trade-off. When you use a cloud service, you get instant, basically infinite scale. You pay as you go, and you don't have to manage a single server. It's amazing. The catch? Well, at huge volumes, it can start to get pricey, and you do give up some of that fine-grained, nerdy control you'd get from building your own custom FFmpeg pipeline. So this brings us right to the core architectural decision that every single video team has to make. It's a choice between two paths. Path 1 is absolute control. You build your own system around FFmpeg where you can tweak every last setting. Path 2 is massive scale. You use a managed service to get up and running fast. There is no single right answer. It's a critical choice you have to make based on your needs. And that really leaves us with the final question to think about. If you were building the next big video platform from scratch today, which way would you go? Would you choose the path of absolute control, or would you opt for the infinite scale of the cloud? It's a tough question, and it's a challenge engineers are solving every single day.